Yeah, thank you very much. Also, thank you very much for inviting me. It's great to be in Brisbane. What I'm going to talk about is joint work with Liede Grotenhuis from the University of Amsterdam, and also Bahare Afshari and Graham Lee, who are both working at the University of Gothenburg. Good, so I'm going to talk, this is a very long title, but I'm going to talk about some proof theory for an intuitionistic modal fixed point logic. Now, thanks to Rahele, we already know what intuitionistic logic is, and I assume that all of you are familiar with modal logic and probably also with modal fixed point logics. So these are essentially modal logics extended by some operators that are characterized by fixed points and express some infinitary behavior. There are many famous examples in philosophy, for example, epistemic logic with the common knowledge operator, or linear time-temporal logic, or more in computer science, you might have PDL or the modal mu calculus. Now we're going to look at an intuitionistic modal logic with the master modality. This is essentially just the reflexive transitive closure of a standard modal box. So this is a very simple intuitionistic modal fixed point logic. The larger project that this is ongoing work, by the way, so nothing published. So the larger picture that this work is in is the following. So there is very little work on intuitionistic modal fixed point logic, but there is a lot of work on classical modal fixed point logics. In particular, there is quite a rich mathematical theory and some tools that have been developed in recent decades include automata that run on infinite words or infinite trees, infinite games, and non-well-founded proofs. And what we're trying to explore is to what extent can these concepts be applied in the intuitionistic setting. And for this talk, I'm going to only talk about the non-well-founded proofs. Now, I'm not sure how familiar you are with the idea of non-well-founded and cyclic proof theory, or whether you've even heard of this. So unless you're telling me that everybody is working with that every day, I'm probably going to give you a quick introduction to what the basic idea is. I assume that you are familiar with sequent calculus, though. So that I'm going to assume.
I don't think are you guys familiar with sequent calculus? Okay, Diana.
You have never seen it? Oh, okay. Well, it's going to be tough.
Proof theory is not a big thing.
Right. Okay. But let me first just start by introducing the logic or the logics that I'm going to talk about. And maybe a short disclaimer. There isn't really the version of intuitionistic modal logic. There are many competing versions in the literature. And I'm not going to go into the discussion of what the right one is or not. I'm just using a standard version that is often used in the literature and that is close to the first order translation of modal logic into first order logic. But I'm not going to talk about like why exactly this one. Good. So here is our syntax. We basically just have the standard syntax of intuitionistic logic with the falsum and atoms, conjunction, disjunction, and the intuitionistic implication. And then we have two modal operators. One is just a standard normal modal box operator. And the second one here is what we call the master modality. Now, please observe that there is no diamond in this language. Of course, in classical logic, box and diamonds are interdefinable, but in intuitionistic logic, this is not the case. So we're looking at a diamond-free version of intuitionistic modal logic. When it comes to evaluating these logics, we're doing this in Kripke models. And as we've seen for intuitionistic logic, we can have Kripke models with like one relation that is a partial order. And we have the same here, but then of course we need a second relation, an arbitrary binary relation to evaluate the modalities. And two comments here, the intuitionistic relation and the modal relation, they don't have any interaction with each other for now. So it is they're basically independent of each other. And then, of course, as is standard in intuitionistic logic, we have a valuation function that assigns to every world a set of propositions, those propositions that are true at this world. And this valuation function has to be monotone with respect to the intuitionistic ordering. So whenever S is smaller or equal to T, we have that the valuation of S is contained in the valuation of T. This goes well with the interpretation of intuitionistic logic that at some point of time, you may know some things, and later on, if you move up, you may know more things, but you cannot forget anything. So in particular, an important property of intuitionistic logic is the monotonicity property, which just extends on this valuation here, saying that if S is smaller or equal to T and S satisfies some formula A, then T will also satisfy that formula A. And of course, for us, we also want to have this monotonicity property. So when it comes to defining the truth conditions for the modal operators, we cannot use the classical truth conditions because they would destroy the monotonicity. So instead, what we will have to do is we will have to evaluate the modal box, for example, by looking at all the worlds that are larger than the current world. So very similar as with the universal quantifier in Rahela's talk. So here, just some technical notation. We denote by R tilde the composition of the smaller equal relation with R, and by R tilde star, just the reflexive and transitive closure of R tilde. And then we can give the standard truth conditions. I only wrote the interesting cases. So for the implication, A implies B is true at world S. If and only if for all larger worlds, the classical implication holds. And similar now, box A is true at world S, if and only for every V such that W has an R tilde relation to V, A holds. So in other words, here at world S, we look at any larger world and then look at any modal successors and check whether A is true here. And of course, since this relation is reflexive, we also look at the modal successors of the world S. And finally, the master modality is just the reflexive transitive closure. So we look at any world V that is accessible over this R tilde star relation. So what we're really doing is we're looking at like up and right paths through our model, right? We take every world, we look at every world that is somehow accessible by going up into over the intuitionistic relation, and then going to the right, and then going up again, and going to the right again, and up and to the right, etc. So any world that is accessible over such finite paths, A has to be true in order for the master modality of A to be true here. So this is the infinite behavior that this operator has. And now it's quite simple to prove the monotonicity lemma because it's just in the semantic definitions. All right. Now, it is quite common in intuitionistic modal logic to add some so-called confluence properties on our models, that is, properties that guide the interaction or introduce some interaction between the intuitionistic and the modal relation. And this is useful because it allows us to simplify the truth conditions for the modalities. And here we're going to look at one specific such confluence property, that is triangle confluence. And basically a triangle model is just a birelational model that satisfies this triangle confluence property, which states whenever W is smaller or equal V, and V has an R relation to U, then W has an R relation to U as well. So whenever this here is the intuitionistic relation, we have this, we also have this. That's why it's called triangle. Now, this is a very nice property because it allows us now for such triangle models to just use the classical truth conditions for the modalities, and we still obtain the monotonicity. So this simplifies to work with this logic. So in particular here, the master modality is now really just the reflexive transitive closure of the relation R. And this is actually quite obvious directly from the definition of these triangle models, we have now two versions of truth conditions, right? Those over arbitrary birelational models and those for triangle models. But of course, triangle models are also birelational models, so we can use the normal truth condition for triangle models as well. And actually, these two truth conditions, they are identical over triangle model. So for any triangle model and any formula, this should be an A, not a phi. A is true in W in the birelational truth conditions, if and only if it is true in the triangle truth conditions. This is pretty obvious because the birelation truth condition just says like, go up and look to the right. And the triangle one says like, yes, but we already see that from here. So nothing happens, really. Good, so we have birelational models, we have triangle models. Let us look at a different or a third version of models, and these are functional ones. And this is just an arbitrary birelational model where R is a partial function. Why are such models interesting? Well, for example, because they allow us to give something like a temporal interpretation of this logic that we're looking at. Since now every world has just one successor, so this is a partial function, but we can also make it with a total function, then every world has a unique successor. This logic is a bit similar to an intuitionistic version of linear time temporal logic. In that case, the box becomes something like a next operator, and the box star becomes something like a henceforth. From now on, in every future time step, this formula will be true. I will later say more about this interpretation because there are some clear weaknesses to see this as a temporal logic, but for now, this is just a comment. All right, so let us define three logics. For me, a logic now is just a set of valid formulas. So first of all, IMK is the set of valid formulas over birelational models. IMT, the set of valid formulas over triangle models, and IMF is the set of valid formulas over functional models. And these are the three logics for these talks that we're interested in. Now, from our previous observations, we already see some relations between these logics, namely IMK is both contained in IMT and IMF. However, and this is maybe more interesting, the opposite directions of these inclusions hold as well. That is, all these three sets of valid formulas are actually identical. Now, the first equation between valid formulas over arbitrary birelational models and over triangle models isn't really new or something surprising. This has already been observed in the case of intuitionistic modal logic by Visser, among others, I think. So it's not really a big surprise that this also holds when you add the master modality. The second equation that is more interesting between IMK and IMF, because this essentially states that this logic is too weak to distinguish between models that have an arbitrary relation and models that have a partial function, which at least to me was rather a surprise that this is really not something that we can distinguish with. And in fact, we could look at birelational models with a theoretic relation, and then we would get the same equality with functional models where the relation is actually a total function. All right, so this equality will be a result from the proof theoretic work that I want to talk about now. Right, so but this is the logic, and our goal is now to find out what kind of, how can we build non-well-founded and cyclic proof systems for such logics, and in particular proof soundness and completeness. Yes, please.
Is this also when we were to take the standard fucking model the final consequence, like logic has anything that's inference, do you still get involved? Was it only true theory?
I think you still do, yes. But I would have to think a bit about it, but I think you still do. All right, so let's talk about non-well-founded proofs. And I'm going to try to give some idea on the whiteboard. So, as I mentioned before, this master modality is a fixed point operator. In particular, it's characterized as the greatest fixed point of this propositional function P that maps P onto A and box P. Right. So to argue about the master modality in semantics, we will require induction to talk about it. Right? We have to talk about every world that is reachable, so we'll have to do induction on these paths. So if we build a proof system for such a logic, we will require a proof system that has some formal counterpart of induction. And the standard way of doing this is by setting up a sequent calculus and adding an induction rule to it. However, this has a downside, and the downside is essentially the induction. So if you've ever done induction in just a normal math course, you know that very often, if you want to prove something inductively, you actually can't, because your induction hypothesis is too weak. And what you have to do is what is called induction strengthening. You have to actually prove a stronger statement in order to prove the weaker one. So a simple example is, suppose we prove by induction that the sum of 1 to n, 1 over, let's say k here, k squared is smaller than 2. Right. So we want to prove this by induction. So the base case is trivial, and now we have the induction hypothesis. So we go to the inductive step, but now we figure out we can't prove it. But because everything the induction hypothesis here tells us is that this sum is smaller or equal to 2. But now if we're adding to this sum 1 over n plus 1 squared, we don't know whether we go over 2 or not. So in fact, what we have to do is we have to strengthen the induction hypothesis. Namely, we instead want to prove the following statement: 2 minus 1 over n. Right. And now if we do the proof, it will actually work with some computation. You will figure out that in the induction step, this is still smaller than this. And then this, of course, implies the weaker statement that we actually want to prove. However, for such an induction, finding the right strengthening, this is not like logically derived from the original statement, right? This is kind of, we're just guessing and we're finding out the right way to do it. Now, if we do this formally in a system that has an induction rule, something similar happens. Usually when we add induction rules, our system is no longer analytic. So generally, if you have a sequent calculus rule with some premise and some conclusion, we call this rule analytic if every formula that occurs in the premise is actually a subformula of a formula occurring in the conclusion. So when you do proof search, that is when you read it bottom up, and we start with some sequent and we're searching for a proof by just backwards applying rules, being analytic is very useful because every formula that might occur in a proof already occurs as a subformula in the conclusion at the root. But if we're not analytic, then in order to do proof search, we will have to guess formulas. And this is obviously impossible because there are infinitely many in general to guess. And this is what often happens when we add an induction rule, because the induction rule, the presence, makes the system non-analytic, and we have to guess something like a strengthening of an induction rule, which is a bad thing for a proof system. So in the presence of modal fixed point logic, one way to circumvent this problem is to instead of having an induction rule look at so-called non-well-founded proofs. And what is a non-well-founded proof? It's essentially a formal counterpart of a proof by infinite descent. Is that something you are familiar with, proofs by infinite descents? It's something you've all seen, but maybe not under this name. It's essentially a special case of proof by contradiction. And the idea is that you obtain a contradiction by contradicting the well-foundedness of some well-order. Basically, you want to prove something about all natural numbers, that no natural number has a property P. So you say, suppose there is one, and then you show, okay, but then it's a strictly smaller one as well, which with this property. But then you can just repeat it infinitely many often, and this is obviously then infinite, strictly decreasing chains of natural number, which doesn't work. Another famous example is square root of 2 is irrational. So suppose it is rational, then we might write it as P divided by Q. And now we do some number theoretic shenanigans, and we realize, okay, but it is also equals P prime divided by Q prime for P prime strictly smaller P and Q prime strictly smaller Q. And these are natural numbers, right? And then we just do it infinitely often until, and we have a proof by infinite descent, once again, a contradiction. All right, so if we want to provide a formal counterpart for such proofs by infinite descents, well, what's going to happen is that these proofs are going to become infinite, right? Because after all, this is an infinite non-well-founded chain. And this is exactly what a non-well-founded proof is. It is a normal sequent calculus proof, so a tree labeled by sequence, but some of the branches are allowed to be infinitely long. Now, in order to avoid vicious infinitary reasoning, because obviously not every infinitary branch is a good branch that shows some valid reasoning, we have to impose some so-called global soundness conditions on these infinitary branches. I will call them for this talk global progress conditions. This is some condition the entire branch has to satisfy in order to be deemed correct. What this global progress condition is very much depends on the logic. But for example, in here, what we would get in such a proof is an infinite chain when we start with P divided by Q, and then there are some steps, and then we're basically back at P divided by Q, but for strictly smaller ones. So the progress here would be that we go somewhere through a rule which strictly decreases these two numbers. But in modal fixed point logic, the progress is pretty different. I'm going to show you the progress conditions once I show you the calculus. I'm not going to explain why exactly it's this progress condition. It's quite technical and takes a long time. But you will have to believe me that this is a good progress condition. All right, so essentially, instead of using induction and being non-analytic, we might use non-well-founded proofs. And very often with non-well-founded proofs, we can set up an analytic calculus. The price that we have to pay, of course, is that our proofs become infinite. However, this can often be remedied by turning non-well-founded proofs into cyclic proofs, which is essentially a finite representation of some non-well-founded proofs. But I'm going to talk about this later if there's enough time. So for now, let's just look at non-well-founded proofs. And what we did is we built a non-well-founded sequent calculus for this logic of intuitionistic master modality, which is called NIM. So here are the technical details. First of all, a sequent is just an expression of the form gamma arrow delta, where gamma and delta are finite sets of formulas. In particular, in intuitionistic logic, it is usual to have delta to be single conclusion. We don't do that. We have a multi-conclusion on the right side. And the interpretation of a sequent is standard, so it's just a conjunction of all the formulas on the left. This should be a normal implication, implying the disjunction of all the formula on the right. So let's look at the rules. First of all, there's a second slide with rules. This is just a standard multi-conclusion sequence calculus for intuitionistic logic. So we have two axioms, the identity axiom and the falsum axiom, which just says, well, A arrow A is always valid, so it doesn't have any premises. And then we have the standard rules for conjunction, disjunction, and implication. Now, it is standard to read rules top down. So this here is the premise, and this is the conclusion. But since we're going to do some proof search later, I will usually read rules bottom up. So this is maybe a bit confusing, but I will still call the lower part conclusion. But we're usually reading it bottom up. So as an example, maybe the interesting case, the only rule which isn't the same as in classical propositional logic is the implication right rule. Namely, if you read it bottom up, you see here that we have the formula A implies B and some set of side formulas delta, and this set is lost when moving to the premise. Right, so we weaken away this set, and this is needed so that we cannot prove the law of excluded middle, which is not valid in intuitionistic logic. Now, more interestingly, here are the modal rules, and they are standard as in classical modal logic. So we have a box rule, which can only be applied if we have a boxed formula on the right side. Now that I notice they are not quite as in classical modal logic. First of all, notice that there are no diamonds in the language. That's why there is no diamond in this rule. And second, observe that also here in this modal rule, the delta gets deleted when moving from the conclusion to the premise. Which part? So there, the diamond or? Oh, yes, yes, yeah, A, box A, right? So this formula has to be present, otherwise the box rule cannot be applied. Oh, yes, bottom up. Sorry, I'm always thinking bottom up, yeah, to apply rules, not top down, yes, yes. Gamma might be empty. It doesn't matter whether there are box formulas, right? And once again, we have to delete the delta when moving from the conclusion to the premise, because this is very similar as in the implication rule. So think of the soundness condition for these rules, which means if the conclusion is invalid, then the premise is, right? So if the conclusion here is invalid, we have to falsify A implies B, but A implies B falsified means we need to go to some larger world where A is true and B is false. And moving from the world which falsifies this sequence to a world which falsifies this here, then we need to get rid of the delta, because if delta is falsified in the lower world, it might no longer be falsified in the higher world. And the same with the modalities. If we have a world which falsifies the conclusion here, then in order to find a world which falsifies the premise, we have to go up, which means we're losing the delta. And then we have to take a modal step, which means we're also losing here the sigma. Yeah, exactly. Exactly. Because this says, okay, every formula in box gamma is true. So whenever I go up and right over a modal step, the formula is true in this world, right?
The box is essentially like the reason we don't do it, we have
Yeah.
in the intuition.
Exactly.
Essentially, box insisting you have one.
Yeah. And the sequence, if they're falsified, means the left-hand side is satisfied at the world and the right-hand side falsified, right? All right, and then we have these rules for the master modality, and they are essentially just expressing that the fixed point, namely that master modality of A is equivalent to A and box star A. Right? So this is what the rules are doing. On the left-hand side, this is just A and box star A, and also on the right-hand side, but the conjunction rule has already been applied. Also notice that here we go from box star A to a formula which is larger because it has an additional box. So this allows us to make branches infinitely long. We have box star A, we go to box star A. Later we go through a modality rule and we're back at box star A, so we can just repeat it and make it infinitely long. All right. Now let us define the global condition on the infinite branches. And in order to do so, let us first define what a derivation is. This is not a proof. This is something like a pre-proof. So under derivation, we just understand a finite or an infinite tree whose nodes are labeled according to the rules of our calculus, and the root is labeled by the sequent S. Right. So no conditions on what the leaves should be or the infinite branches. This is just generally it should be a tree formed by the rules of our calculus. Now, a path through such a derivation is exactly what you expect, namely just an infinite sequence of nodes of the tree, such that for every node, rho I plus 1 is a direct successor in the tree. And these paths have to be infinite. Good. Now this global condition is formulated with so-called formula traces. And this is a bit technical now, but we just have to go through it. So try to take something with it, and otherwise it's not super important for the rest of the talk. So the idea is we have like an infinite path in our proof tree, and now we're looking at a formula trace. And a formula trace is essentially just tracing the development of one formula through that path. So it is an infinite sequence of formulas for which the following things hold. First of all, the ith formula always occurs on the right-hand side of the sequence that labels the ith node in the path. Second, if AI is a principal formula, principal just means here in the rule that it's the formula that the rule operates on. Once again, reading from bottom to top. If the rule does not operate on this formula, it's called a side formula. So if the formula is a principal formula of the rule instance at rho I, then the next formula is its residual formula. And once again, residual is just the formula that follows. Once it's operated, it's decomposed into some formulas, and the decomposed formula are the residual ones of the principal. So here in A and B is the principal formula of this rule, then B and A here are residual formulas. And similarly in the implication, A implies B is principal, hence A and B are residual. And all the other formulas are side. And this is the condition. If it's a side formula and we pass through a rule, then nothing happens to the formula. I will give an example just on the next slide, so which will hopefully make it clear. Okay, so we have these formula traces on infinite paths, and we call such a formula trace good, and this is going to be the global progress, if there are infinitely many elements of the trace, infinitely many AIs, which are the principal formula of a box star right rule, and AI plus 1 is the residual formula in the right premise. So essentially, our infinite path passes infinitely often through the box star right rule, and each time, or infinitely many times, the trace formula is this box star A, and then the next trace formula is the box star A. This is a good trace. And the proof in our calculus is then a derivation in which every leaf is an axiom and every infinite branch contains a path with a good formula trace. All right, so I hope that makes a little bit of sense. Let's just look at an example. This here is a proof of the sequence box star A implies box star A or B. So we start once again from the bottom to the top. We first apply the box star left rule, which turns box star A into A and box star A. Then we can apply the box star right rule, which makes the branch split. On the right-hand side here, we have A or B. This goes to an axiom. And on the left-hand side, sorry. And on the right-hand side, we have the unfolding box star, A or B. And now we can apply a box rule, and we're basically back at the start, right? So I put 3 dots on top of it. That just means we can repeat this infinitely often now. And observe that this derivation here has only one infinite branch, namely the one that always follows this here on the right-hand side. And this infinite branch contains a path with a good formula trace, namely the trace that is generated by just following the development of box star A or B, right? So we start here. Now it's a side formula, so nothing happens to it. Now it's principal, so we go to the right premise. Then it's a box rule, so it's principal again. We're here, and then it just goes on. So this goes infinitely long, and it passes infinitely often through this box star right rule. So this is deemed to be correct proof of this sequent. All right. Now here, a quick result. This system can quite easily be shown to be sound with respect to the class of birelational models, and hence also with respect to the class of triangle models and functional models. I'm not going to go into the soundness proof, but just observe that the soundness proof for such a calculus isn't as easy as for a normal finitary calculus, because we can't just proceed by induction on the length of the derivation. Instead, what the way this proceeds is by a proof by infinite descent. So the idea is we take some sequent that has a proof and assume towards contradiction it has a counter model. And then what we can do is we can assign a natural number to every sequent occurring in this proof. And then we can build an infinitary path that goes through this proof, in which the natural number assigned to the sequence decreases strictly infinitely many times, which then gives the contradiction that we want. So this shows also the close connection to proofs by infinite descent. What I want to talk about is how to prove completeness for such a calculus.
Here, the definition of a proof is actually
Yes. Exactly. Yeah. All right. So how do we prove completeness for such a calculus? Well, there are multiple ways, but the way that we're using here is by proof search. And the idea is basically of proof search that we want to find some procedure that, given as a sequent, checks whether this sequent has a proof. Right? So this is something that is often done in proof theory. In particular, for like classical propositional logic, proof search is very simple, because in this calculus, every rule you have is invertible, and therefore all you can do when searching for the proof is just applying rules in any order, and you will figure out whether it has a proof or not. Because nothing, due to the invertibility, nothing can go wrong. When it's valid, it stays valid no matter what you do. However, in our case, with intuitionistic logic, it's not quite that simple. Because if you look at the rules here, for example, the implication right rule, this rule is not invertible. So invertible just means if the conclusion is provable if and only if the premise is, right? So you can just apply them upwards without any risk. But here the implication right rule is not invertible because we're losing this set delta. So it might be that this sequent here is valid, but the reason for its validity lies in delta. And now we're applying the implication right rule. We're losing it, so this is no longer valid. And similarly, the box rule here is also not invertible. So when we want to do proof search, we have to be a bit smart about how to search for this proof. We cannot just apply rules in any order, right? A second problem is, of course, that our proofs are infinitely long. So we need some way of making sure that we really check every possible case. And the good news is we don't have to check every possible proof of a sequence. It suffices to make a somewhat intelligible search. And this search is essentially formalized or done as follows. The idea is that in order to do, given some sequent, gamma arrow delta, we will build a very large tree. We will build this tree by applying rules from our calculus. And since there are non-invertible rules in our calculus, we want to delay the application of these non-invertible rules as long as possible. So what we're going to do is we're going to start by putting the sequence that we want to check at the root. And then we're going to first apply the invertible rules to this sequence as long as we can. That means as long as still when applying an invertible rule, something new is added to the sequence. But at some point after finitely many steps, we have essentially saturated this sequence. So we have built some tree, and now here we've come to a sequence that is saturated. Now until here we know it's safe, because we only applied invertible rules. So if this is valid, then this is valid too. But now the only rules here that we can apply that make something new with our calculus is an implication right rule or a box rule, the non-invertible ones. But of course, we don't know which one we should apply. So what we're going to do is we're going to add a new rule. This is the so-called choice rule that simply applies every possible combination of these non-invertible rules to this sequence. So say if we have two implications here on the right, then the choice rule will have one premise where we have applied this implication rule. So one premise of the form gamma prime phi arrow psi. And there will be one premise where we have applied the implication rule to this implication. So we're going to have this. And similarly, for every box rule on the right, there's going to be one premise that corresponds to applying the modal rule to that box. So this is not a rule from our calculus, but this makes our tree branch in a lot of branches, and each of them correspond to a possible choice that we could have done in order to prove this sequence. And now once we're here, we just start applying invertible rules again until we're saturated, and then we do the same thing again. And this goes on infinitely long. So this gives us a really big tree. And now our claim is, well, if this sequence is provable, then we can find some subtree that is actually a proof in this tree. And this subtree can be found by going always to these choice rules and just choosing one of the premises, because this then corresponds to a proof. However, if the sequence is not provable, then what we're going to do is we're going to find a subtree from which we can build a counter model of this sequence. So how do we find these subtrees? Well, by using some nice tools from game theory, essentially. So I don't want to go into details here, but essentially, this huge tree can be an arena of an infinitary two-player games. And then what you have are two players, a prover and a refuter. And the prover tries to prove the sequence and the refuter tries to refute it. So each position in this tree you can assign to one of the players. in particular, these choice rules here are going to be position of prover, and then you can let them play against each other. And basically, this game, if we set it up like that, happens to be a Borel game. So there's a famous theorem that states that one of the players is going to have a winning strategy for this game. And the winning strategy, the strategy tree of the winning strategy will be a proof if the prover has a winning strategy and otherwise a refutation. That is a counter model from this. Good. So here, just as an example, if we want to prove completeness of our calculus with respect to triangle models, then the C rule would look like something like this. So we have saturated our sequent, and now we have a bunch of implications on the right and a bunch of box rules, and we apply this choice rule, and then this gives us a lot of premises depending on to what formula we apply a rule. Good, but now suppose we have such a huge tree. And now we want to prove the completeness. So if prover happens to have a winning strategy, it's quite trivial to show that this is actually a proof. So the more interesting case is what happens if refuter has a winning strategy. That is, we get some subtree here of this tree, which is given by the winning strategy of refuter. So how does this subtree look like? Basically, we have invertible rules that have just one premise, and we have invertible rules that have like two premises, right? So here there will be some branching. Now the idea is, refuter is trying to show that this sequence is not valid. So whenever we have an invertible rule that branches into two premises, it suffices for refuter to pick one, right? Because he only has to show one of the premises is not provable. So whenever we have an invertible rule that branches, refuter will have exactly, this will be a position for refuter, and he can choose to which of the premises he wants to move. However, if we come to a C rule here, then this is not going to be a position of refuter, this is going to be a position of prover. Why? Because there are multiple ways how to apply a rule, and all the prover has to do is to say, well, one possible application preserves the validity. So in our in this refutation here, the refuter will have to keep all of the possible branching trees here present in his refutation. Because for any possible choice of prover, he has to have an answer, right? So the tree is going to be just one branch until we're going to come to a refutation, to a C rule, and then it's going to include all the possible branches here from the C rule, and then it's going to be one branch again until we're at the next C rule. And from such a thing, we can now actually define a triangle model that refutes the sequent. Here, the idea is the whole branch that we get until we reach a C rule is going to correspond to one world. So we're going to merge all these sequences into one world. And we're going to define a valuation by simply saying, look at all the formulas that occur on the left-hand side of the sequence and satisfy every proposition that occurs there, right? So this whole thing here will correspond to a single world in our model. Now we have the C rule, right? So we have a saturated sequence here, which is falsified at this world here. And now we need to falsify the right-hand side, right? So falsified, the left-hand side is true, the right-hand side is false. So in particular, we need to falsify each of these implications. And since implications, we have to look higher up, we need to create a world which falsifies phi implies psi. And in order to do that, Well, we can go to this premise here, right? Because here, phi has come to the left-hand side and psi is on the right. So the branch that corresponds to the left hand, to this premise here, will become a new world that is an intuitionistic successor of the current world. And then once again, we define the valuation as before, and this valuation will guarantee that here phi is satisfied and psi is falsified. Similarly, for every other premise that corresponds to applying one of these implication rules. But then, of course, we also have the box formulas. And not very surprisingly, the box formulas correspond to adding in a modal successor into the Kripke model. So if we want to satisfy one of these box formulas here, then essentially what this means is we have to find some modal successor which falsifies this formula. So each of the premises, right, that we're getting up here corresponds to adding in one modal successor into our model. And this is basically already it. We can now, given that we define all these formally, we can now define such a counter model from a refutation by following this procedure. And then we can prove that this counter model is actually a counter model to this sequent. Right. So here things are pretty simple. Of course, there is one thing that I forgot to say. We need to make sure that this model is a triangle model. So we have to add in some intuitionistic, some modal relations whenever we go up here to make sure that we're actually getting a triangle model. But that's not hard actually to do.
So you said you basically like the stick, like it's not.
Yes.
But that closure is not in any way related to the
Yes, in this simple case, it's as simple as just adding in the relations. Yeah, this works well by the way the rules are set up, because the relevant information, namely the box formulas on the left, are preserved when going to an intuitionistic successor. Right. There are much more complicated cases. One is, so this gives us completeness for triangle models. One is if we want to show that the same calculus is also complete for functional models, because what happens here is whenever we have come to one of these saturated sequence and we have multiple box formulas, we can now only use one of the box formulas to create the modal successor. And for all the other box formulas, we have to delay the decision of when to falsify them. So this means we will have to keep them in the premises of the rule, and we need to make sure that we treat them all eventually in our proof search tree. But I think I'm not going to go into that because there's actually a question. Oh, yes, I scared one person away. Nice. Right. Okay, so just if we look at it, we can now do the same procedure with proof search for also functional models. There it's a bit more complicated because it's just harder to build this counter model from a refutation. But it works. So what we're getting is the theorem that this calculus is actually complete with respect to the classes of triangle models and of functional models, and hence also with respect to the classes of birelational models. So we're getting what I said earlier, namely this chain of equality. Now, maybe some good properties, because it's not only our goal to, say, build a proof system for this logic, but we also hope that we gain some insight of how to build proof systems generally for intuitionistic modal fixed point logics in a more modular way. And there are some good news about this. So this proof system is quite modular. For example, we can easily turn our logic into a multimodal logic by just adding in more boxes, which then gives a natural interpretation for intuitionistic common knowledge logic, where the different boxes are now just knowledge operators, and the box star becomes a common knowledge operator. And it's actually quite straightforward to adapt the system to this case and therefore obtain a non-well-founded calculus for intuitionistic common knowledge, which is analytic. If one looks at such common knowledge logic, then it's also natural to say, well, we would like to add frame conditions, such as reflexivity or transitivity to our logic, because one could say, well, knowledge should be reflexive or whatever. And we can account quite easily as well for that. So our methods are robust, for example, for adding reflexivity or seriality and transitivity, and probably also more. We haven't checked. We don't know the case for S5. But basically, all you have to do for these things is just add the corresponding rule for reflexivity, and the proof search is not going to change much. And also the soundness is not going to change much. You just need to check one extra case. So this is quite modular. Moreover, we can also turn this calculus into a single conclusion calculus, which is more natural in intuitionistic logic. And once again, this works, it's not quite as easy as it works by co-inductive argument. Finally, and this can also be turned into a cyclic system, and I will say quickly something about that on the next slide. However, there are also some problems. In particular, I mentioned that this logic over functional models could be regarded as a temporal logic, right? However, there is a bit of a problem here, because suppose we have a temporal logic with two operators. One is a next operator that says in the next time step something is true. That would be our box. And one is the henceforth operator, which says from now on something will always be true. That would be the master modality. However, in a functional model, we don't really have a next operator, because we still have to look at all the worlds above. So if we want to evaluate in some point next A, then it doesn't just suffice to look at this world. We also have to look at all the worlds above and their temporal successors. And this means that some of the axioms that you would like to be fulfilled in a temporal logics are not fulfilled. For example, next A or B implies next A or next B. So in a temporal logic, if you say in the next time step A or B is true, well, then either A or B is true. But this is not the case for us, because it could be that here A is true and up here B is true. Then next A or B is satisfied, but not next A and not next B. So in a way, this is not really a good interpretation of temporal logic. This could be saved by adding stronger confluence properties on our logic. In particular, forward confluence, which just says whenever we are in this situation, then there exists a world up here and the diagram commutes. Right, so once again, R and smaller equal. This is also a common confluence property in intuitionistic modal logic. If we add this, then we can turn our logic into a more standard version of intuitionistic temporal logic. However, adding this changes a lot of things. First of all, it smuggles a diamond into our language and collapses the diamond in the box into the next operator. And this has quite some changes then. For example, it is no longer true that in the logic with this confluence property is going to be the same logic as the logic without confluence properties. Because, for example, this formula is going to be satisfied, or it's going to be valid here, but not in general. Moreover, so we have some work on building non-well-founded calculi for logics like this, and the whole proof search argument and everything becomes much more difficult. Mostly because when we built the counter model, then exactly this happens what James mentioned before, namely, we cannot just fill in the relation easily when we add in new worlds, right? So we're going to build worlds like intuitionistic successors and temporal successors, and then we're going to build here a temporal successor, and now we have to add in this relation. And this is now not easily possible anymore in this case, because this world here and this world here, they correspond to completely distinct branches in the proof search tree. So we might make different choices here and here. And in order to deal with this, you need much more machinery in the proof system. Also, this logic then doesn't admit a simple cyclic system, unfortunately. Okay, I think I should finish, right? It's been quite a while.
Frankly, we have the moment to
Yes, but I see also some tired faces. I just say 2 minutes or something about. I'm not going to explain much, but just a few sentences about cyclic proofs. So what we have now managed to do is giving a non-well-founded proof system, which is analytic. So this is a clear advantage over the systems with an induction rule, but at the price of making the proof infinite. And therefore, the goal is that this is just an intermediate step, and we can actually turn this infinitary calculus into a cyclic calculus. And the idea of a cyclic calculus is that it is just a finite representation of an infinitary proof. So if you look at the example that I showed before of this non-well-founded proof, the sequent, we notice that at this node here, we are just at the same place again as here, right? So instead of building an actual infinitely long proof, we might just add a loop from here back down to the root and say, just repeat, right? And then what we actually gain here is a finite representation of this non-well-founded tree. Now, in order to make it really finite, there is one difficulty. Namely, in the non-well-founded case, in order to check that it's a sound proof, we had to check all these infinitary branches, whether they contain good traces, right? Now, here for cyclic proofs, we basically have to do the same thing. But if we say, take a cyclic proof and just check every infinite branch, then we're just at the same as with the non-well-founded proof. Because of course, you might have a cyclic proof that looks something like this. And now you're going to have infinitary branches that not only go all the way to the left or all the way to the right, but also left, right, right? By just going up here, down, then up here, down. So if we just say every infinite branch of a cyclic proof has a good trace, then we're just at the same situation, more or less, as with the non-well-founded case. So what we really want to do is find a local progress condition in these branches instead of a global one. All we want to do is whenever we have such a loop, we want to check the finite path between the two nodes that are identified and say this finite path has to satisfy some property to ensure that the proof is sound. I call it local because now it's just on these finite things and no longer on the global. In particular, this local progress condition that this path here satisfies needs to ensure that all the infinite paths that pass through here are correct. So not only the one that goes all the way like this, but also the one that goes like this, right? So they need to be stronger. And in fact, these cyclic proofs, they really just correspond to regular non-well-founded proofs, if that says something to you. So the question is, we can prove completeness for non-well-founded proofs. Can we prove completeness for regular non-well-founded proofs? Because if yes, we can turn it into a cyclic system. And for this logic, it turns out this is possible. It's actually quite easy to turn the non-well-founded system into a cyclic one, but you need some extra technical work on the calculus. And this is not something I'm going to go into it. So I'm just going to skip that. But it is a nice additional property that actually we can turn it, and thus we get an analytic and a finite calculus for this logic, which is a clear advantage then over an induction rule. All right, so 3 final remarks. The first is, what is the complexity of proof search for the cyclic system? So how difficult is it to check whether a sequence has a cyclic proof? We haven't investigated that, but I would be quite confident to say it's at most exponential for this logic. Probably not better, but who knows? Then the second is, can we start to generalize this method to more expressive fixed point logics, which is something we're going to certainly try to do in the future. And then, of course, how can we deal if we add a diamond to the language, which is what a lot of people working in intuitionistic modal logic would say, like, you got to add a diamond. And in fact, adding the diamond here for now causes some problems. We haven't really investigated it, but it certainly makes things harder. So this would be some ideas for how to continue this work. Okay, so let me stop here. I hope that wasn't too proof theoretical. Thank you for your attention.